possible mistake in the marking of the answers to the exam. In one of the questions, I asked if this is aromatic, and I got those questions from a very nice textbook written by a very famous American organic chemist, and I just copied down the questions without thinking about them. And in this book, there is that question, is this stuff aromatic? And the answer key says yes. And of course there are 4n plus 2 electrons in it, but somebody pointed out to me that maybe these hydrogens interfere with one another and so it wouldn't be flat. And so what I did is I looked up the literature to see what's known about this compound. And I found, to my dismay, that in fact nobody's ever made this compound, so nothing is known about it. So those of you who said that this is not aromatic, it's only a few of you, and therefore didn't get the 1 mark, whatever it was, 2 marks for that question. I suspect that most of you didn't notice that possibility, and I'm not even convinced that it is a strong possibility, but I have to be fair. And those of you who lost the 2 marks on that question, if you come and see me in my office and show me your exam, I will give you the 2 marks and adjust your final mark appropriately. So having dealt with that, I must now continue talking about organic chemistry, and what I was up to last time is I was telling you, let's get some quiet. You guys must be the noisiest class we've had here for years. There's no Dean's medal or Dean's honour list for being the noisiest class. So let's just pipe down and be a bit quieter. In fact, be totally quiet. What I have to do is to continue talking about what I was dealing with at the end of the last lecture. And at the end of the last lecture, I was dealing with benzylic hydrogens. And I told you there was a special reaction for benzylic hydrogens, and that was the case of halogenation. You could take a compound with a benzylic hydrogen and you could treat it with N-bromosuccinimide, and that would then give you the result of replacing one of the benzylic hydrogens by bromine. And you could do a similar thing with N-chlorosuccinimide, but most importantly, you could do a similar thing with chlorine. If you heat toluene with chlorine, this is toluene, it has 3 benzylic hydrogens, and if you add enough chlorine, you can replace first one of them, and so your first product will be this compound, which is called benzyl chloride. And if you continue the process, you can replace the second benzylic hydrogen and finally a third benzylic hydrogen. So this is just a reaction of benzylic hydrogens, and remember these reactions are radical reactions, and the reason why they go is that you can write resonance structures for a benzylic radical, and I'll just write one of them. So here's a resonance structure for one of the resonance structures for a benzylic radical, but I can move the electron here, have the radical here, and I can move the electron this way and have the radical there. So it's because of the formation of a stabilized species, in this case a benzylic radical, that these reactions work the way they do. But it's exactly the same explanation that accounts for the fact that if you take propene, this has 3 arylic hydrogens. You can replace one of those arylic hydrogens with bromine by using NBS. Now, the fact that you can generate a stabilized species here, in this case a benzylic radical, that fact that you generate a stabilized species is not limited to radicals. You could also generate a stabilized plus charge, for example. And that explains the reaction that I'm going to tell you about now. You see, what I've done in the last few lectures is to take benzene and to tell you you can carry out electrophilic aromatic substitution. That is to say, you can replace one of the hydrogens on benzene by a nitro group or SO3H or an alkyl group or an acyl group or a chlorine or a bromine. And then I went on to, now I gave you the mechanism for those processes. Then I went on to tell you that if you've got one substituent on the benzene ring, the ring becomes more reactive or less reactive compared with benzene. And once one substituent is in, when you put in the second substituent, it goes in certain places, either onto a para or meta. And I then explained to you how that happens. Then I moved on. I'm still dealing with benzene compounds, but I started to tell you a little bit about what happens to carbon atoms attached to the benzene ring. And what I just erased on the board, toluene and bromination or chlorination, I'm telling you that if you've got an alkyl group attached to a benzene ring, the benzylic position, that is to say the carbon directly attached to the benzene ring, has some special reactivity. Because if you break one of the CH bonds for such a carbon, you get a resonance stabilized radical, as I just showed you. Now I'm going to show you a few more reactions of the side chain, as we call it, of benzene, to show you how this resonance business, where you can make a stabilized benzylic radical or stabilized carbocation, for example, even a stabilized carbanion, how that allows you to interpret what is going on. So let us take this compound and treat it with HBr in the presence of a peroxide. This is a peroxide. And what happens? What you will find happens is that you get this compound. In other words, bromine adds to one end of the double bond, and hydrogen adds to the other end of the double bond. But the question is, why does bromine add to that end and not the other one? Well, once one thinks about the mechanism, one will realize how this happens. What happens is the peroxide, where R can be various things, you don't have to worry about that, on heating, breaks into, well, two of them, two radicals of that type. Now, what these radicals do is they attack HBr to give you a bromine radical. And that bromine radical attacks this double bond. But it can attack that double bond in two ways. Supposing am I writing too low here? Can you guys see this? To the end of the double bond that I showed, the radical that's formed is a benzylic radical. And not more than 5 minutes ago, I spent some time telling you that benzylic radicals are resonance stabilized. So they're easy to form. If the bromine added to the other end of the double bond, the radical that you get would not be a benzylic radical, and it would not be resonance stabilized. So that bromine atom has a choice. It can either generate a resonance stabilized radical, or it can generate a non-resonance stabilized radical. And the formation of the resonance stabilized radical is just another way of saying that it forms the more stable product. It forms the thing that's easier to form. It's easier to form a resonance stabilized radical than it is to form a non-resonance stabilized radical. And so now we get this as this radical here is an intermediate species, and what that does is it attacks the hydrogen to give you the observed product where that hydrogen is the one that comes from the HBr plus Br dot, another bromine radical. And you can easily guess what that bromine radical does. It adds to another molecule of the double bond compound. And of course, once again, it adds to the end of the double bond that gives you the preferred radical, the more stable radical. So this business of stabilizing a benzylic radical accounts very nicely for this addition of HBr to this double bond under radical conditions. And you know it's going to be radical conditions because you start off by adding a peroxide. And when you add a peroxide to something, it's almost always used as a radical initiator. The reason why that is the case is that if a peroxide has a weak bond between oxygen and oxygen. And if you heat it, that bond breaks. And it breaks in a way to give two oxygen-centered radicals, two pieces with a radical and oxygen. Once you generate those radicals, they will proceed to do the sorts of things that I've shown. Now you can do this reaction under different conditions, in the absence of a radical initiator. We can do that to get a different product. But once again, the nature of that product is very easy to understand on the basis that of the various possibilities that could occur, the one that will occur is the one that gives a resonance stabilized intermediate. So let me clean the board and show you. You better write this down again because that's it. Supposing we just do it under ionic conditions, what you will get is now that compound. So the bromine adds now to the benzylic position. So what's going on? Well, what's going on is that the electrons come out of the double bond in two ways. They can either come out to give a benzylic carbocation, which is resonance stabilized, or if they come out the other way, they'll give a carbocation that's not resonance stabilized. And so of the two possibilities, the one that leads to the resonance stabilized species is the one that is actually followed. Now there's another, I'll give you a moment to write that down. Just let me make clear to you that if the reaction went the other way, and it doesn't go this way, supposing it went like that, what you would get is this, which then would be attacked by a bromine ion in that position. But this radical is not resonance stabilized. Whereas if the electrons come out the other end of the double bond, like this, then what you get is a resonance stabilized carbocation, because I can bring electron density out of the ring and put plus charge on the ring, and I can write several resonance structures. I'm not going to do that. So in this case, the way the reaction goes is via the resonance stabilized carbocation. Now there's another type of reaction of alkyl chains attached to benzene rings, which I need to tell you about. And that is a subject called oxidation of the side chain. If you treat toluene with alkaline potassium permanganate, you oxidize this carbon to a carboxylic acid group. This substance is called benzoic acid. And if you have a longer chain, just say that, for example, and do the same thing. What happens is a little bit strange, because you break that bond there and you oxidize this carbon, the benzoic, let me just send that arrow. You oxidize the benzylic position to a carboxylic acid group, COOH. Now you know from what I told you that benzylic hydrogens are rather reactive. I've given you a radical example, I've given you a carbocation example. So it shouldn't be surprising that the benzylic position is the one that's modified in this experiment. We won't go into the mechanism, it's pretty complicated, probably not, definitely not fully known. But if you have alkyl groups attached to benzene and you oxidize the compound, the benzylic carbons are oxidized to carboxyl groups. So, for example, supposing you got some compound, and all you know is it's a benzene ring with a couple of alkyl chains on it. And supposing, I won't let you run the NMR spectrum, so you can't work out where the alkyl chains are. It's Christmas Day and the NMR machine isn't working, and so you want to find out what it is. You can do a very simple experiment. You can oxidize it. And of course, each of the alkyl chains will be converted into a carboxylic acid group. And this particular carboxylic acid, with the two carboxyl groups on adjacent carbons, that's a known compound. So you can take a melting point, look up in the literature what the melting point is supposed to be, and if the carboxylic acid groups are meta or para, the melting points are different. So just by doing an oxidation and then taking the melting point, you can find out what you've got, and you can go home and have a nice, well-deserved Christmas dinner. Of course, it's much easier just to run the NMR spectrum. You can work that out, you can work out the position. Okay. What I want to do before leaving this subject is just to make a little summary of the properties of benzylic and allylic halides and compare those properties with halides that are not benzylic. So if you take these various halides, a methyl halide, straight to an alkyl halide, a secondary halide, these things react mainly by SN2 reactions in nucleophilic substitution. If you have a tertiary halide, or a tertiary halide having a benzene ring, or a tertiary halide that's a allylic, they act mainly by SN1. And these, primary benzylic, or a secondary benzylic, or a primary allylic, or a secondary allylic, they can react either by SN1 or by SN2. And which way they react depends upon the reaction and the conditions. So that's a very brief summary of the reactivity of these compounds. And what I'd like to do is I'd like to do one worked example for you. And that example would be this. get 2 alcohols from this experiment, and what you should do as a homework problem is number 15.9, and it's also 15.19, and it's also 15.19 in the 9th edition. There is one last reaction of benzene rings that I need to tell you about. It was developed by an Australian working in England, in Oxford, and he was told by his professor not to work on this reaction. His professor was very busy. His professor was Sir Robert Robinson. The professor was very, very busy advising the government, because they couldn't keep an eye on what this fellow was doing. And this fellow went ahead and worked on this reaction. The reason why the professor told him not to work on this reaction is that the reaction was first recorded in a patent put out by a company for which the professor was a consultant, and he didn't want to be accused of stealing ideas from the company. But this Australian student working in Oxford in England by the name of Arthur Birch decided that this reaction was just too good not to develop. So he went ahead and developed it and got a huge number of results. And he told the professor when he next saw him, the results were so good that there was no way you could sort of throw the results away and not publish them. And the reaction is called the Birch reduction. And what it is a method of partially reducing benzene rings. You take benzene and you dissolve it in liquid ammonia containing at least an equivalent of an alcohol, such as tertiary butanol or ethanol. And you then add sodium. And if you do that, what you get is that diene. It turns out that that's a very, very useful reaction. And we don't, in this course, have an opportunity to give many examples as to why it's useful, but I need to show you what happens. What happens is electrons come ultimately from the sodium and add to the benzene ring. And so if you add an electron to the benzene ring, what I'm going to do is I'm going to use that resonance structure and I'm going to emphasize 2 of the electrons. And if I add an electron to the benzene ring, I can get a species like this. Now in your mind, this isn't how it happens, but in your mind you could imagine that one of these electrons decides, has an argument with the other electron, doesn't want to talk to it, so it decides to be on that carbon, this electron decides to be on that carbon, and then there's an electron added to one of the carbons, so now there are 2 there, minus charge, and just 1 there. So that's the first thing that happens. Now I can write a resonance structure for this. I can write a resonance structure, and I'm going to put the little 2 electrons there. And then I'm going to tell you that the alcohol provides a proton. So now I have that resonance structure. And now yet another electron is added to the system. And so now I have that. And this now pulls off another proton from the alcohol. And so that is the product. Now there are a lot of questions about this that should be in your mind. And one is, I have chosen particular resonance structures. Especially I've chosen this one. And then I could write resonance structures for this, in which the radical is over there or over there. But I haven't. I've left it like this, and I've chosen this resonance structure for the carbanion. And again, I could have the negative charge here or here. But I haven't done that. I've left it like that, and I've made then this dihydrobenzene derivative, in which the hydrogens have added para to one another. Now, there are some reasons why this occurs, but they're way beyond the content of this course. All you need to know is, if you take a benzene ring and you treat it with sodium and liquid ammonia containing a little bit of alcohol, you will add hydrogens in the 2 para positions. You end up with that. Now, let me show you just one example of what you can do with this sort of chemistry. So this is the Birch reduction. Supposing we take this compound, this is now a monosubstituted benzene, and we're going to add the 2 electrons via the Birch reduction. Now, what I've told you so far is that the electrons are added in the para position. But where on this ring will they add? Well, the answer is fairly easy. You know from previous lectures that this pushes electron density into the ring. That's why it's an orthopara director. So if you're going to add electron density, you can add electrons, it doesn't go here. It goes somewhere else. And there's only one other place you can add the electrons if you're going to add them in a para position. And that's here and here. Of course, it's the same as if you added it there and there by symmetry. So let's add the hydrogen. So we'll say this is Birch reduction. Birch reduction. Now I've added 2 hydrogens para to one another, but I have avoided adding them at a position that has an electron donating group. And that's very reasonable. If you're going to add electrons to some substance, you add it to a place that is, relatively speaking, deficient in electron density. So you don't add it to the carbon carrying the electron donating group. So now I have this compound. If you take this compound and treat it with acid, first that. And then, if there's water present, which there is, the water will come in there. And so now, you generated this, that loses a proton. This picks up a proton on a different oxygen. Oops. Lone pair comes along, pushes that out. And the proton comes off. And something else can happen with acid. The double bond can move into conjugation. So that's quite a complicated sequence for you. What we've done is we've started off with a benzene ring. We've done a Birch reduction to add two hydrogens parallel to one another, and we add them in such a way that we avoid the carbon carrying an electron withdrawing group. So now we get this, which is called an enol ether. An enol ether. An enol ether is just oxygen attached to double bond. And enol ethers are sensitive to acid. And if you treat an enol ether with acid, the electrons move in the way that I've shown to pick up a proton on carbon. Then water comes in to give you a new species that transfers a proton from this oxygen to the other oxygen. So now you're here, and now the electron pushes out the methoxy group to give finally a protonated ketone, and that's the product. And if you continue the reaction, this double bond moves into conjugation. And the way it moves into conjugation is easy to understand, because if you follow through those arrows, you'll get this. So this Birch reduction method is a very, very good way of making cyclohexenones. Cyclohexenones. Cyclohexenones are six-membered cyclic ketones. And you know from last year ketones is a carbonyl compound with two carbons on the carbonyl carbon. And this one is a cyclohexenone, so there's an ene in it, a double bond. So this Birch reduction is a very good way of making that compound and many other compounds, because you can have other substituents around the ring. Provided they're not incompatible with the conditions of the Birch reduction, you can make substituted cyclohexenones. But we don't have time to go through all these examples. All that I'd like you to do, I will put up some problems, and you should do problem 15.24, 15.25, 15.26, 15.27, and 15.32 and 15.34. And those are all the same numbers in the ninth edition. So it's 10th and 9th edition. And if you do those, you'll be well practiced in this business of manipulating benzene rings, either to do electrophilic aromatic substitution on the benzene ring, without any substituents, or when there's already one substituent, or dealing with reactions at the benzylic position, or even dealing with a Birch reduction. And now I have to move on to the next chapter, which is chapter 11, which is about alcohols and also ethers. Okay, what I've written up on the board is just 3 examples of alcohols and ethers, 1 ether and 2 alcohols, that occur in nature. This stuff is the flavor of peppermint. This material is vanilla. And this material is in something called fennel. So these compounds actually occur in flavors that we use. Now, I wrote up the general structure of an alcohol. The general structure of an alcohol is an OH group attached to carbon. And you can see that in menthol, I do have an OH group attached to carbon. It actually happens to be a cyclohexyl unit. In vanillin, I do have an OH group attached to carbon, but that carbon is part of a benzene ring. And these are rather special alcohols. They're normally called, not wrong, they're always called phenols. And phenols we will deal with separately. So I'm only going to talk about today, in the next lecture or so, about alcohols in which the OH is joined to an aliphatic carbon and not to a benzene carbon. And then ethers are compounds in which an oxygen is joined to 2 carbons. And you can see a relationship. I'm not going to draw the correct shape, but if you have that compound, which I hope you recognize as water, if you replace one of the carbons, you get an alcohol. If you replace one of the hydrogens, you get an alcohol. And if you replace both of the hydrogens, you get an ether. So in a sense, these things can be regarded as derivatives of water. They're certainly structurally related to water. And in fact, you can make them from water. You can take water and replace one of the hydrogens by an alkyl group. Dead easy to go from water to MEOH, and from MEOH to an ether. Now we'll rule out the business of phenols because, as I said, I'm not going to talk about phenols just yet. Now, as is usual, we need to first talk a little bit about how to name these compounds so that you can describe the sorts of substances that you're dealing with. Now, the way of naming alcohols, there are two ways. For a small number of alcohols, there are so-called trivial names, and then for more complicated alcohols, there are systematic